There are more than 1 billion vehicles on the road today. And almost every single one built after the year 2000 has something in common, something you can't see, can't hear, and probably never think about. A nervous system. Underneath the sheet metal, behind the dashboard, screwed into the engine block, dozens of sensors are working right now. Measuring, reporting, deciding, and feeding information to the brain of the car, a small computer called the engine control unit. The ECU. Before the 2000s, cars were largely mechanical. You pushed the accelerator, a cable pulled the throttle. The engine mixed fuel and air using a carburetor, a passive, mechanical device that had no idea what the temperature was, what the altitude was, or whether the engine was knocking. It was guesswork. Educated guesswork, but guesswork. Then came OBD-II. On-board diagnostics, the second generation. By the late 1990s it was mandatory across the United States, and by the mid-2000s it had swept across Europe, Japan, and most of the world. For the first time, every car had a standardized diagnostic port, a window into the car's soul, and every car was required to monitor its own emissions, engine health, and sensor performance in real time. That single regulation changed everything. Because to monitor itself, the car needs sensors. And to add sensors, engineers had to rethink every system on the vehicle, from the air entering the intake to the exhaust leaving the tailpipe. Today, a mid-range family car, nothing exotic, carries between 60 and 100 sensors. A premium vehicle might have over 200. They talk to each other through a network called the CAN bus, the controller area network, sending data packets dozens of times per second. The car has become, in the truest sense, a computer on wheels. In this video, we are going to meet those sensors. Not just what they are, but what they do, what happens when they go wrong, and what the data looks like when you plug in a scan tool and peer inside. We'll start under the hood with the sensors that manage combustion and keep your engine alive. Then we'll move to the chassis, the sensors that quietly save lives every day. Then to the eyes of the car, the cameras, radar, and ultrasonic systems that are turning ordinary vehicles into semi-autonomous machines. And finally, we'll look ahead at where sensor technology is heading next. Whether you're a car enthusiast, a mechanic, or someone who simply wants to understand the machine you drive every day, by the end of this, you'll never look at your dashboard the same way again. Let's go. Pop the hood of any car built after 2000, a Toyota, a Ford, a Volkswagen, and underneath all that metal and plastic, there's an invisible nervous system. A web of sensors, constantly measuring, constantly reporting, feeding data to the ECU. Think of the ECU as an army general. But a general is only as good as the intelligence reports coming in. Those reports are your engine sensors. Without them, the engine is flying blind. Let's meet them, one by one. The MF sensor, mass airflow. Every combustion engine needs two things to make power, fuel and air. The MF sensor sits in the intake pipe and measures exactly how much air is entering the engine, in grams per second. The ECU takes that reading and calculates how much fuel to inject. More air, more fuel. Less air, less fuel. A precise, real-time calculation happening hundreds of times per minute. When it fails, the dirty or failing MF sends wrong readings. The ECU either overfuels or starves the engine. You'll notice rough idle, poor acceleration, and noticeably worse fuel economy. On a scan tool, MF readings that don't track with throttle input are a dead giveaway. The MAP sensor, manifold absolute pressure. Some engines use a MAP sensor instead of, or alongside, AMF. While the MAF measures air mass directly, the MAP measures pressure inside the intake manifold. The ECU then calculates air density from that pressure combined with air temperature. When it fails, the ECU can't calculate load correctly, you get poor throttle response, misfires, and the engine running excessively rich or lean. Oxygen sensors, upstream and downstream. Modern cars have at least 2 oxygen sensors per exhaust bank. The upstream sensor, sitting before the catalytic converter, monitors the actual air-fuel mixture coming out of combustion. Rich or lean. The ECU uses this for real-time fuel correction, what engineers call closed-loop control. The downstream sensor, positioned after the catalytic converter, monitors converter efficiency. It tells the ECU whether the cat is actually cleaning the exhaust. When either fails, the upstream failure throws fuel trim off completely, the engine runs inefficiently and you'll almost always get a check engine light. Downstream failure won't affect running quality much, but you've lost visibility on converter health, and in markets with emissions testing, that's a failed test. On a scan tool, watch your short-term and long-term fuel trim values. Anything beyond plus or minus 10% tells you the engine is fighting to correct itself. The knock sensor. One of the most underappreciated sensors on the block. Literally. Engine knock, also called detonation, is when the air-fuel mixture ignites prematurely before the spark plug fires. It sounds like a faint metallic rattle. Left unchecked, it destroys pistons, wears bearings, and can crack engine components. The knock sensor is essentially a microphone bolted to the engine block. It listens for that specific vibration frequency. The moment it detects knock, it signals the ECU, which immediately retards ignition timing, pulling it back to stop the knock. Here's a real-world scenario. Imagine pulling up your OBD scan data and seeing this, your knock correct LAN value is sitting at 22.5 degrees of crank angle retard, that's the maximum the ECU can pull timing back. And your knock feedback is showing active correction at -3 degrees. What this tells you is that the ECU has been fighting knock so persistently, over weeks or months, that it has maxed out its long-term retard table. Timing retard means less aggressive combustion, less power, more fuel burn, and a drop in fuel economy you'll feel every time you fill up. The likely cause? Carbon deposits on intake valves and piston crowns, a known issue on high-mileage engines. Carbon absorbs heat, creates hot spots, and triggers detonation even on premium fuel. The fix isn't just replacing sensors, it's addressing the root cause, carbon cleaning, fuel system treatment, and a spark plug inspection. When the knock sensor itself fails, the ECU loses its early warning system. To protect the engine, it defaults to permanently conservative timing, robbing you of power and efficiency even when knock isn't happening. Crankshaft and camshaft position sensors. These two work as a pair. The crankshaft position sensor tells the ECU exactly where the pistons are in their cycle, essential for knowing when to fire the spark plug and when to inject fuel. The camshaft position sensor tracks valve timing, allowing the ECU to synchronize injection with intake valve opening. When either fails, the engine may crank but refuse to start, or cut out suddenly at speed, one of the more alarming failures a driver can experience. On a scan tool, you'll see RPM signal dropout or erratic crankshaft data. This is also why cam and crank sensor faults will sometimes produce no-start conditions with zero fault codes. The ECU simply has nothing to act on. Coolant temperature sensor, LECT, cold engines run differently from warm ones. The ECT tells the ECU the engine's temperature, affecting fuel mixture, idle speed, ignition timing, and when the cooling fan activates. When it fails, the ECU may think the engine is perpetually cold, flooding it with excess fuel in open-loop enrichment. Fuel economy tanks. Emissions spike. You may notice black smoke from the exhaust on warm starts. On a scan tool, a healthy ECT reading after a full warm-up should sit between 80 and 95 degrees Celsius on most modern engines. Throttle position sensor, TPMS. On modern drive-by-wire cars, which is most post-2000s vehicles, there's no physical cable connecting your foot to the throttle. The TPMS reads your accelerator pedal position and sends that data to the ECU, which then electronically controls the throttle butterfly. When it fails, a hesitation, surging, or limp mode, where the car limits itself to protect the drivetrain. On a scan tool, the TPMS reading should move smoothly and proportionally from 0 to 100% as you press the pedal. Any dead spots or jumps? Suspect the sensor. Here's the bigger picture. None of these sensors work in isolation. They are all feeding data into the ECU simultaneously, every 10 to 100 milliseconds. The ECU processes that data and makes thousands of tiny adjustments to fuel, timing, and airflow in real time. And that's exactly what your OBD scan tool sees when you plug in. Freeze frames. Live data streams. Fuel trim trends. Knock correction values. Temperature curves. A scan tool doesn't just read fault codes, it reads the story your engine is telling. And if you know what each sensor does, you can read that story too. Coming up next, we step outside the engine bay. Because the sensors that save your life aren't under the hood. They're in your wheels, your brakes, your chassis, and they're making split-second decisions you'll never even feel. It's a rainy Tuesday evening. You're doing 90 kilometers per hour on a wet highway when the car in front of you brakes hard. You react, but a fraction too late. Your tires begin to lose grip. In that instant, before you've even processed what's happening, your car already has. And it's already responded. That split-second intervention. It came from your chassis sensors. Wheel speed sensors, ABS. Every wheel on a modern car has a wheel speed sensor. These measure how fast each wheel is spinning, individually, dozens of times per second. The data feeds directly into the anti-lock braking system, or ABS. When you brake hard, ABS compares wheel speeds. If one wheel decelerates faster than the others, the early signal of a lockup, the system rapidly pulses that brake caliper, preventing the tire from fully locking. The result, you maintain steering control even under emergency braking. When it fails, ABS and traction control warning lights illuminate, and those systems are disabled. Braking still works, but without the protection. On a scan tool, individual wheel speed channels are visible, and a dead channel points directly to the faulty sensor. Your rate and lateral acceleration sensors is electronic stability control. These are the sensors that caught you in that wet highway scenario. The yaw rate sensor measures rotation around the car's vertical axis, is the car spinning. The lateral G sensor measures sideways force, is the car sliding. Together, they power electronic stability control, ESC. Every millisecond, ESC compares where the car is going versus where you're steering. If those two things don't match, if the car is understeering off the road, or oversteering into a spin, ESC selectively brakes individual wheels to bring the vehicle back in line. All without any input from you. Studies consistently show ESC reduces fatal single vehicle crashes by 30 to 50%. Since 2011, it has been mandatory on all new vehicles sold in the European Union. The US followed, as did Australia, Japan, and much of the rest of the world. When it fails, stability control and traction control are disabled. You're back to raw physics with no electronic safety net. Airbag impact sensors. Airbag sensors, also called crash sensors or accelerometers, are positioned at the front, sides, and structural pillars of the car. They measure sudden deceleration with extreme precision. In a crash, they trigger in under 30 milliseconds, faster than you can blink, deploying the airbag at exactly the right moment. Too early. The airbag deploys unnecessarily. Too late. It doesn't protect the occupant at the right point in the collision sequence. The calibration has to be exact. When sensors fail or become misaligned, the airbag warning light illuminates. And an airbag system with a fault will not deploy in a crash. This is one warning light that should never be ignored. Tire pressure monitoring, a TPMS. Each wheel contains a small radio transmitter that monitors tire pressure and temperature in real time. If pressure drops, from a slow puncture, temperature change, or valve leak, the sensor broadcasts a signal to the car's receiver, which triggers the TPMS warning on your dashboard. This matters more than it sounds. An underinflated tire runs hotter, wears unevenly, increases fuel consumption, and can experience sudden blowout at motorway speeds. TPMS has been mandatory in the US since 2008 and in the EU since 2014. Battery life on TPMS sensors is typically 5 to 10 years, after which the whole sensor usually needs replacing, not just the battery. Rain and light sensors. The rain sensor uses an infrared beam bounced off the inside of the windscreen. Dry glass reflects the beam clearly. Water droplets scatter it. The more scatter, the harder the wipers work. Automatically. The ambient light sensor adjusts instrument brightness and triggers headlights at dusk, a small convenience that is, for many drivers, simply invisible. Until it stops working. Parking sensors, ultrasonic. Parking sensors work exactly like a bat using echolocation. The sensor emits a high-frequency sound pulse, above human hearing, and listens for the echo bouncing back from nearby objects. The time between pulse and echo tells the system the distance. Closer object, a faster return, faster beeping. These same ultrasonic sensors underpin low-speed automatic braking systems and, in more advanced cars, fully automatic parking assist. What's critical to understand about all these sensors is this: they don't work alone. Wheel speed, gear rate, steering angle, throttle position, and brake pressure data all flow into the same control network. The car's safety systems are constantly cross-referencing this data, building a real-time model of what the vehicle is doing and what it should be doing. That network, that cooperation between sensors, is the reason modern cars are dramatically safer than the vehicles of 30 years ago. Not because drivers got better. Because the car got smarter. But we are not done yet. Because the next generation of sensors doesn't just monitor the car, they monitor the world around it. The sensors we've covered so far react to what the car itself is doing, measuring its own speed, temperature, pressure, rotation. But starting in the 2010s, a new class of sensors arrived. Sensors that look outward. Sensors that perceive the world, other vehicles, lane markings, pedestrians, road signs, and use that information to assist, warn, or even take over from the driver. These are ADAS sensors. Advanced Driver Assistance Systems. And they represent the single biggest leap in automotive technology since the seatbelt. Radar, short and long range. Radar works exactly as it does in aviation and weather forecasting, by emitting radio waves and measuring the reflections. Long-range radar, typically mounted at the front of the vehicle, can track objects up to 200 meters ahead. It's the backbone of adaptive cruise control, the system that keeps your car a set distance from the vehicle in front, automatically adjusting speed. Short-range radar covers the blind spots and rear corners of the vehicle, powering blind spot monitoring and rear cross-traffic alert. Radar's great advantage is that it works in conditions that defeat cameras, darkness, rain, fog, and dust. It doesn't see color or lane markings, but it reliably detects objects and measures their relative speed with high accuracy. Cameras, monocular and stereo. Cameras are the sensors closest to human vision. A single forward-facing camera, monocular, is now standard equipment on most new cars. It reads lane markings for lane keep assist. It recognizes speed limit signs for intelligent speed assistance. It detects pedestrians and cyclists for automatic emergency braking. More advanced systems use stereo cameras, two lenses set apart like human eyes, which can calculate true depth, not just flat images. This is how some systems can accurately judge the height of an obstacle, determining, for instance, whether a low barrier can safely be driven over. Cameras are cheap, high resolution, and rich in information. But they struggle in low light, heavy rain, and direct sun glare. Which is exactly why they don't work alone. Ultrasonic sensors, close-range awareness. Think of ultrasonic sensors as the car's short-range tactile sense, like fingertips filling the space around it. At speeds below roughly 10 km per hour, these are the primary sensors for detecting obstacles during parking maneuvers. In more sophisticated systems, ultrasonic data feeds into automated parking assist, where the car steers itself into a space while you control only the accelerator and brake. In fully automated parking modes available in some premium vehicles, you can exit the car and park it remotely from a smartphone. LiDAR, light detection and ranging. LiDAR fires rapid pulses of laser light, millions of pulses per second, and builds a precise three-dimensional map of everything around the car. Unlike radar, LiDAR creates a detailed point cloud, a genuine 3D picture of the environment. Currently, LiDAR is predominantly found on robotaxi and autonomous research vehicles rather than mainstream consumer cars. The cost has been falling rapidly, and several manufacturers have announced production vehicles with integrated LiDAR for higher-level autonomous driving. Volvo's EX90 and some Mercedes models have launched with it. This is the sensor that will define the next decade. Sensor fusion, PY1 is never enough. Here's the fundamental challenge of ADAS, no single sensor type is sufficient on its own. Radar detects objects but can't read signs. Cameras read signs but fail in fog. LiDAR builds detailed maps but is expensive and can struggle with rain. Ultrasonic works close up but is blind at distance. The answer is sensor fusion, combining data from all sources simultaneously and letting the vehicle's central processor reconcile them into a single, reliable picture of reality. Tesla does this without LiDAR, using camera and radar data combined with neural network processing. Waymo uses all four. The debate over the right sensor mix for full autonomy is one of the defining engineering arguments of our time. What's not debatable is where all of this is heading. And that's exactly where we are going next, into the near future of what sensors in your car will be able to do. We've come a long way. From the early 2000s, when OBD-II standardization first forced manufacturers to make their cars self-aware, to today, where a family SUV carries radar, cameras, ultrasonic arrays, and a constellation of engine and chassis sensors that never stop talking to each other. But the sensor revolution hasn't peaked. Not even close. What's coming? In-cabin biometric sensors. The next frontier is inside the car, monitoring not the road, but the driver. In-cabin cameras using infrared light are already appearing in production vehicles, tracking eye movement, blink rate, and head position to detect drowsiness and distraction. Some systems can detect microsleeps, brief, dangerous losses of consciousness, before the driver themselves is even aware it happened. Beyond that, steering wheel sensors are being developed that can monitor heart rate and detect signs of cardiac stress. Some manufacturers are exploring seat sensors that detect breathing patterns. The goal, a car that knows your physiological state and can respond, slowing down, pulling over, or alerting emergency services, when you cannot. V2X, vehicles talking to everything. V2X stands for vehicle to everything. It's a communication technology that turns the car itself into a sensor node within a broader smart city network. Your car broadcasts its position, speed, and direction, and receives the same data from every other equipped vehicle and piece of infrastructure around it. Traffic lights that tell your car when they'll turn green. Roadworks signs that broadcast their position directly to your navigation. Emergency vehicles that announce their approach before you can hear them. V2X promises a world where accidents caused by hidden hazards and delayed human reaction become increasingly rare. Europe and China are actively deploying V2X infrastructure. The US is advancing standards. This technology is coming, the question is only how fast. AI and the meaning of sensor data. Perhaps the most profound shift isn't in the sensors themselves, it's in what happens to their data. Artificial intelligence is changing how sensor data is interpreted. Where a traditional ECU follows fixed rules, if NOx sensor reads above threshold, retard timing by X degrees, AI systems learn from patterns across millions of kilometers of real-world driving. They can predict component failure before it happens. Detect driving style changes that might indicate a medical event. Optimize fuel injection strategies in real time based on learned behavior, not just current readings. The sensor is still just a sensor, but the intelligence listening to it is becoming something genuinely new. Here's what I want to leave you with. You don't need a robotaxi or a premium EV to start understanding your car's sensor data. Every car built after 1996 has an OBD-II port, usually under the dashboard on the driver's side. A Bluetooth OBD scanner costs as little as $20. And apps like Talk Pro, OBD Fusion, or Car Scanner will show you live data, your fuel trims, your coolant temperature, your throttle position, your knock retard, right on your phone. When you can read that data, you stop being a passenger in your own car. You become someone who understands what the machine is telling you. And that knowledge, whether you're diagnosing a fault, planning maintenance, or just satisfying curiosity, is genuinely powerful. If you found this video useful, we are doing a follow-up episode on exactly how to read and interpret OBD scan data, what the numbers mean, what to look for, and how to diagnose common faults without ever visiting a workshop. Subscribe so you don't miss it. Until then, drive smart, maintain often, and remember, your car is always talking. You just have to know how to listen.